Exploring the Solar System Part 2, using spacecraft to explore the planets and other objects in our solar system. So I'll be asking the question, how do we get there? What do the spacecraft do once we got there? And how do we get information back? In principle, any scientific information, but most people are interested in how do we get images back to Earth, because we want to see what the spacecraft sees. And then again, we can ask the question, where next? I thought I'd start by just summarizing how many spacecraft have been sent out into the solar system. I started adding them up in the fingers of one hand and realized that's not enough, and then the fingers of two hands, still not enough. And it wasn't until I actually produced a list I realized just how many there have been. Now, I realize you probably can't read the writing here, but that's how many spacecraft we have sent into space. Hundreds, absolutely hundreds. The last one on this particular list is Europa Clipper, which was a mission launched a few months ago. I think this list is up to date, but I'm going to clearly have to add to it every once in a while. So we have sent spacecraft all over the solar system. Getting, for instance, to our nearest neighbour, going from Earth to Mars, is relatively straightforward. If we imagine Earth in a circular orbit around the Sun and Mars in a circular orbit around the Sun, this is not to scale and not particularly accurate, but it gives us the idea of how we can go from Earth to Mars. The most efficient way is to follow that blue ellipse. It's an ellipse which goes around the Sun, and at its furthest from the Sun, it coincides with the Mars orbit, and as it's closest to the Sun, it coincides with the Earth's orbit. It's called the Hohmann transfer. You might have heard that if you're a fan of the film The Martian. So for our nearest neighbour, a relatively simple elliptical transfer from one orbit to the other. But back in the 1960s, it was realised that if we want to go further afield, we can actually use the gravity of other planets. For instance, we can fly past Jupiter, notice that kick, that dog leg, and a sudden increase in velocity. We can use a gravity assist, as it's called, or sometimes called a slingshot maneuver. We actually use the velocity of the planet as we fly by to give us a kick and send us on even faster in the direction that we want to go. That means we can explore the outer solar system not only faster because we get an extra kick in speed, so we arrive at Saturn or Uranus or Neptune even faster, but because we're not firing any rockets and only using the gravity of another planet, it means we save on fuel, which means the spacecraft we send can have more scientific equipment rather than more fuel. This was used for Voyager 1, it was also used for Voyager 2, where here again the pink shows the spacecraft. It was launched from Earth, it got a gravity assist from Jupiter, which sent it on to Saturn, and then as it passed Saturn it got a gravity assist there, which flung it out even further to the outer solar system, to Uranus, where it got another gravity assist, and finally sent it on to Neptune. So that spacecraft was able to visit 4 planets in the outer solar system without using any fuel in terms of maneuvering. It was simply a question of flying past the planet at the right time, launching at precisely the right time, so you could fly past these planets which happened to be in the right part of the solar system during the 1970s and 80s to get this so-called grand tour of the outer solar system. A wonderful idea. So let's ask ourselves about images. This is one of the first images taken of another body in the solar system. I'm not sure if you can guess which one it is. If I tell you the spacecraft that took the image, then you'll know. This was taken by Luna 3. So this is an image of the far side of the moon taken in the 1950s. We can clean it up a little bit with image processing, but you can see it's not a very high resolution image, just a few splodges. But when you think about how this image was taken, it's quite remarkable, because in the 1950s we didn't have any digital cameras. So how do you take a picture like this? Well, it was taken on film, good old-fashioned film emulsion, which was then exposed and then sent to a chemical laboratory inside the spacecraft where it was developed and fixed and dried. And then the image was scanned by a cathode ray tube spot scanning over the image, and then a photomultiplier, a little light sensor behind it, recorded how much light was going through the image. And that signal from the photomultiplier was then transmitted back to Earth, where they reconstructed the image, a bit like a fax machine would construct an image from electronic signal. When we look at a modern version of the far side of the moon taken with a NASA probe some 50 years later, you realize that apart from the fact the NASA image is much higher resolution, notice that all the basic features in that 1950s image were basically right. The dark spots, the light spots were correct. A very different surface compared to the near side of the moon, which is the one we always see. The far side of the moon couldn't be imaged from Earth, and therefore we required spacecraft to get that first image. Digital technology came along a few years later. In the mid-60s, we had spacecraft like the Mariner spacecraft. Mariner 4 had the world's first digital camera. Not the first digital camera used on a spacecraft, the first digital camera. So the digital camera you've got in your mobile phone basically is the end of a 50-year pedigree, or more than 50-year pedigree, because digital imaging started with spacecraft. And they've got smaller and smaller and smaller so that they can now fit in a mobile phone. The data from the camera, as it was flying past Mars, was stored on a tape loop. And after the encounter with Mars, after all of the information had been recorded, the tape loop continued running and was read back, and the read back was then transmitted back to Earth. Again, we can take the original image and clean it up a little bit with image processing, and you can see we can clearly see craters on the surface of Mars. So this was the first image taken with a digital camera back in the mid-1960s. Since then, we've effectively explored every planet in the solar system and quite a few other objects as well. We've also explored dwarf planets and asteroids and moons. I'm not going to have time to talk about all spacecraft missions, but let's just pick a couple out as an example. The Cassini mission explored Saturn and its rings and its moons, and it was there from 2004 until 2017. The bottom right image here gives you an idea of the size of the Cassini spacecraft relative to a person standing next to it. So you can see these spacecraft are many meters high. And I'm not going to go through all the numbers on the left-hand side, but some of these numbers are worth reminding ourselves about. Billions of miles travelled from Earth to Saturn. Millions of commands executed. Various commands from mission control telling it where it should be steering, which particular moon it should be exploring, which direction it needs to point its cameras to get an image of the ring system, for instance. 500,000 images taken over its lifetime. It was eventually crashed into Saturn. That might sound a bit odd. Why don't you just let it die and just leave it orbiting the planet? They deliberately crashed it into Saturn because the moons of Saturn, and indeed the moons of Jupiter, are possible harbours of life. It is thought that the moons might conceivably have started life. The planets themselves unlikely, Jupiter not likely, Saturn not likely, but moons of Jupiter and moons of Saturn are the right sort of environment for life to evolve. So to make sure this spacecraft never contaminated any of those moons unwittingly, it was crashed into Saturn itself. This is a picture taken from Earth using the Hubble Space Telescope, a nice image, but with Cassini we can see so much more detail. For instance, if we look at the rings with Cassini, we can see exquisite amount of detail. And the individual particles, none of these rings are solid, they are simply huge numbers of tiny particles. If we look very closely, it starts to look like the grooves of a long playing record. The ring system is exceptionally flat. It may be something like 250,000 kilometers in diameter, but its thickness can be measured in meters, no more than 1 kilometre at most. When the sun is coming from the right direction, the sun actually casts shadows. So although most of the ring system is very flat, there do appear to be some parts of the ring system that appear to be a little bit bumpy, and hence casting these very long shadows when the sun is coming in at a very shallow angle. Even these bumps are only 1 kilometre or so high, indicating that most of the ring system is considerably flatter than that. One thing we can't get from Earth is this view. This is the view of Saturn with the sun behind it. So in other words, Cassini has flown into Saturn's shadow. Now the sun is shining through the ring system from behind. That's actually quite useful, because when light shines through a system like this from behind, the amount of scattering of the light tells us what sort of size the particles are. So we can get an idea of how big the ring particles are by looking at the various brightness of the rings when the sun is at various angles directly behind the planet itself. As well as Cassini taking images of Saturn and the rings and the moons, there was also a second spacecraft called Huygens. It's this one sitting on the side there. Huygens was released in 2005 for a particular task, and that was to enter the atmosphere of the moon Titan. Titan has got a very thick atmosphere, and hence we can't see what the surface is like. So sending a spacecraft through the atmosphere and taking images as it went, so it's on a parachute to slow its descent through the atmosphere. As it came in towards the surface, it was taking images as it went. So now we've got an idea of what Titan looks like. Previously, the atmosphere too thick and too hazy to see. But now we know that Titan is a world in its own right. It has mountains, it has lakes, it has rivers, it has clouds, it has rain. Pretty much like Manchester, basically. But now we've got an idea of what this moon looks like. We should not think of moons as being desolate, dull objects. Some moons are very, very interesting in their own right. Another example of a mission to the outer solar system was Juno. Back in 2016, it was sent to look at Jupiter. Again, some amazing numbers. Billions of miles launched, billions of miles travelled, millions of commands executed in terms of where it was supposed to go, what it was supposed to be imaging, data it was supposed to be collecting. Jupiter itself is a rather stripy planet. If we take the planet and unwrap it, then we see these various bands. These are winds travelling different directions, a bit like the sort of trade winds on Earth, but these are very much stronger winds. Why are these bands different colours? Why are some of them white, some of them orangey colour? We think that's because the colours are a function of which particular elements and compounds are present. Perhaps the white indicates ammonia ices. Perhaps the brown indicates phosphor compounds that are being dredged up from lower altitudes. Because the winds travel in different directions, it looks like the Great Red Spot, which is a storm system resulting from winds travelling in different directions on both sides. It looks like that's a storm system that has been raging for hundreds of years. Why is it that a storm system on Jupiter can last so long, whereas storms on Earth tend to finish after a few hours or a few days? Juno is spending a lot of its time in a large orbit at distance from Jupiter, but every once in a while it swoops down over the cloud tops. Here we get an amazingly detailed view. Some of the white flashes you can see there are lightning. This is a time lapse taken over an hour or two, compressed into less than a minute. But you can see amazing detail in the cloud tops as it swoops over the surface, and then it starts to go in a very stretched orbit, again a long distance away, looking back at the surface. Different colours, different elements, some white spots there appear to be, again, storm systems. If we look at just one still from that movie, again, the amount of detail in these images will keep planetary scientists happy for years. understanding what's going on, understanding the structure, understanding the winds, understanding the storms, understanding what elements are present and what that tells us about Jupiter and its environment. We must remember that the solar system is not just the Sun and 8 planets. For instance, the New Horizons mission was sent to Pluto, which is a dwarf planet on the edge of our solar system, but New Horizons spacecraft kept going after it did a flyby of Pluto, and it's now moving out to the outer realms of the solar system. Beyond Pluto, there's a belt called the Kuiper Belt, which is full of relatively small icy objects, and New Horizons is studying those as it leaves the solar system in much the same way that the Voyager probes in the 1970s are leaving the solar system. But in addition to the planets, there are over 300 moons. Earth has got one, Jupiter and Saturn have got loads between them because they are much more massive bodies. Here's a sample of just a few of them. There's the familiar moon in the bottom right. There's a moon that looks like a pizza. That's Io, one of the moons of Jupiter. Some of the moons look more like the Death Star from Star Wars than they do moons. There's the rather hazy environment of Titan and various other ice moons at the top there. Here's a few of the largest moons shown to scale. Again, there's our moon on the right-hand side. This gives you the impression that you can see here Titan, the large moon of Saturn. This is the one with the hazy atmosphere, and we needed the Huygens spacecraft to go in to tell us what the surface looks like. You can see it looks very hazy, but notice its size. It's huge compared to our moon. And the 4 moons at the top are the biggest moons of Jupiter: Io, Europa, Ganymede and Callisto. Io is a very volcanic moon, looks a little bit like a pizza. It's so close to Jupiter, it's getting stretched, and there's a lot of volcanic activity there. But there's a lot of interest recently about the 3 other moons, the 3 ice moons of Jupiter: Europa, Ganymede and Callisto. They all seem to have ice on the surface, but there is very strong evidence that they have water underneath the ice. In other words, they are water worlds that simply have an ice cap covering the entire planet. If there's a subsurface ocean there, there's the possibility of life. They have the right mix of chemicals. They have water as an agent that brings those chemicals together, and there is an energy source from the nearby Jupiter. And therefore, they are candidates for life having evolved. And that's why there's so much interest in these icy moons. The European Space Agency has sent the mission JUICE. It launched a couple of years ago, Jupiter's icy moons. And NASA have launched a few months ago Europa Clipper, again to get a closer view at these ice moons. How do we get the information back from these spacecraft? Well, up till now, it's been a radio dish on the spacecraft sending radio signals back to an even bigger radio dish on Earth. But recently people have asked, why should we be limited by radio? We can get much higher bandwidth, we can get much faster transmission if instead of using radio, we use lasers. That means we have a laser, possibly a low power laser is all you need, and then you have an optical telescope such as the one shown in the bottom right. That's the Hale telescope with a 5-meter diameter mirror. It's still a large telescope, but it's not the same size as, for instance, a radio telescope seen on the bottom left. So this test was done by a mission sent to an asteroid to study the asteroid. Most of the data was sent back by radio waves, but as a test case, they also tried sending data back via a laser beam pointed back at Earth. What would they send back as a test of a laser transmission? Well, a simple image wouldn't really be a good test, so they decided to send back to Earth a high-definition video, many megabytes of data. The video they chose, well, they figured as we are sending the data on a laser beam, let's send a video of a cat chasing a laser beam. So that's the video they sent, a high-definition video, and even though the spacecraft was at a distance of 50 million kilometers, they still achieved data rates of 260 megabits per second. That's faster than some people can get off their broadband when the server is 10 miles away. So doing that at a distance of 50 million kilometers is very impressive. And even when the spacecraft was at a distance of 400 million kilometers, a huge distance away, they were still getting data rates of 8 megabits per second. Much, 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 much faster than they can possibly get with radio transmissions, which typically would be at least 1,000 times slower. So perhaps in the future, when spacecraft visit all parts of our solar system, they'll be sending data back thousands of times faster. In principle, much higher resolution images, much higher resolution, high definition videos can be sent at fast data rates if we start using lasers. We're not there yet, but that looks like the future. So I've been telling you about various missions. The one in the top right, Cassini, is now no more. Cassini has been crashed into Saturn. In the top left, Bepi Colombo is a mission on its way to the planet Mercury. New Horizons, I've described, is a mission that's leaving the solar system but still taking images as it goes. Juno is still in orbit around Jupiter, though it's coming to the end of its life. And the two latest missions to launch, European Space Agency has sent the JUICE mission to Jupiter's icy moons, and NASA has sent the Europa Clipper to, again, one of the moons or some of the moons of Jupiter. So if you want to know more about missions that have existed in the past and missions that are ongoing for the future, there are a few web resources. I'll make these slides available to you so you don't have to jot these down on the back of a napkin. I'll be giving you the slides in case you want to follow up anything that I've been saying about how we explore the solar system with spacecraft. Thank you again for listening.